Hi, everybody. Welcome to topic 23, central limit theorem with mean. So we talk about this concept back at the beginning of semester where we know it is very difficult to find the true mean of a population. So imagine this whole thing is my population. So the idea we talked about at the beginning of semester was taking a lot of small samples, right? Taking lots and lots and lots of small samples because it's very, very difficult, okay, to get the true mean of the population. So instead, asking everyone, okay, what we can do is taking a lot of small samples. So these small samples, okay, that we take, we're gonna have sample mean for every one of them. So eventually, all these sample mean can actually become a random variable. Okay, so the sample mean X bar can be used to approximate the population mean mu, since it is easier to obtain the sample mean. So if we take different samples from a population, we may obtain different sample means. So using median household income, for example, okay, median household income in the Northeast and the Northwest of the United States is tend to be a little bit higher than other parts of the country. So when we take samples of median household income at the different part of the country, different states, then we're gonna obtain different sample means from every single state. All right. So since a sample mean may be different from different group of samples, then the sample mean will become a random variable. So this topic is about central limit theorem with the mean. Okay, so what's happening here is what we can do is we have another type of distribution. It's called sampling distribution of the sample mean. Okay, sampling distribution of a sample mean X bar is a probability distribution using X bar as the random variable with mean of the X bar and the sigma of the sampling distribution of the sample mean. Okay, so our population mean is actually the sampling distribution of the sample mean, and the standard deviation is the sampling distribution of the sample mean. So if the random variable X is normally distributed, the distribution of the sampling distribution X bar will also be normally distributed with a slight difference. So the blue curve right here is a normally distributed, okay, with the random variable X. So when we take lots and lots and lots of small samples, okay, all those sample means becomes a random variable also, okay? So then those coming from all those samples, we still have a normally distributed curve. We still have a bell curve shape. It just kind of jacks up a little bit higher, okay? And the reason why it goes a little bit higher is because the standard deviation of the sampling distribution of the sample mean X bar is a little bit smaller. Okay, it's a little bit smaller than the regular population standard deviation. That's why the pink graph look a little bit, taller than the blue one. So the blue one is the normal population, okay, standard, normal curve. All right. The pink one is basically the, coming from taking lots and lots of samples, okay? So what is a central limit theorem? For any given population with mean, mu, and a standard deviation sigma, a sampling distribution of the sample means will have the following three characteristics. If either the sample size n is at least 30 or the population is normally distributed. All right. So this sampling distribution, this is a different type of distribution. Okay, it's a sampling distribution about your sample means. The mean of a sampling distribution of the sample mean mu's of X bar. Okay, so this is the mean of the sample distribution equal to the, will equal to the mean of the true population mu. Okay, the standard deviation. So basically what we're saying is, out of all these samples that we took, the mean of the sampling distribution X bar will eventually equal to the true population mean. Okay, so that was the whole concept here. Okay, taking lots and lots and lots of samples. So eventually it will cover up almost all the entire population. The standard deviation of a sampling distribution of the sample mean will equal to, all right, sigma of X bar. So that notation representing the standard deviation of a sampling distribution of sample mean is equal to the true population standard deviation divided by square root of the sample size. The third characteristic, okay, for the central limit theorem says the shape of a sampling distribution of the sample mean will eventually approach that of a normal distribution. Okay, regardless the shape of the population distribution. The larger the sample size, the better the normal distribution approximation will be. Of course, the bigger the sample size, right? That means what? I'm getting closer and closer to the true population. Okay, that's the idea. So again, just like in the previous topic, we're gonna convert, okay, we're gonna convert, into a standard score. So this is a formula for a standard score for a sample mean. So according to a central limit theorem, if either the sample size n is at least 30, or sometimes it will say the population is normally distributed, then a standard score for a sample mean in a sampling distribution is given by the z-score is going to be the X bar, the sample mean. So this is where it is weird. Before, the formula was random variable X minus the mu divided by standard deviation. But our random variable now becomes X bar, the sample mean. All right, so this is going to be the sample mean minus the mean of the sampling distribution X bar divided by the standard deviation of the sampling distribution of the X bar of the sample means is equal to, so look up here, sigma sub X bar is equal to sigma over square root of n. So the formula is a little bit altered, okay? The formula is a little bit altered as compared to the original way how we convert into a z-score. And the reason is the standard deviation is a little bit different, right? The standard deviation is a little bit different. That's what causes, the sampling distribution of the sample mean, that normal curve a little bit taller. So as the sample size increases, okay, this curve, this pink curve will eventually look very much like the blue one. All right, so how do we find probability of the sampling distribution of the sample mean? It's pretty much the same thing as before. We're gonna find the mean of the sampling distribution X bar, which we know by the central limit theorem will eventually equal to the true population mean. Find the standard deviation of the sampling distribution X bar, which is taking the true population standard deviation divided by square root of n, and we're gonna convert into a z-score, and we can use our graphing calculator to find the area. So these problems are slightly different, okay? They sound a little bit slightly different than the one we've been looking at from the previous topic. So let's take a look, okay? So a quality control expert at a battery factory want to test their new batteries. The design engineer claims they have a standard deviation of 62 minutes with a mean life of 606 minutes. So what I mean is, of all the batteries that they make, okay, they found that their mean is 606, standard deviation is about 62 minutes, okay? If the claim is true, all right, then in a sample of 99 batteries. So right now what's happening is they know what their true mean and standard deviation is. So if what they're claiming is true, then they're gonna take a sample, right? Out of that sample of 99 batteries, what is the probability that the mean battery out of that 99 batteries would be greater than 619 minutes? So this 619 minutes is actually the mean battery of that 99, not out of the entire population. All right. So to satisfy the condition of the central limit theorem, is the above scenario has a sample size at least 30 or the population is normally distributed. So the above sample size is 99. So it does satisfy. So here we're gonna say satisfy by sample size at least 30. Okay. All right, list a population mean, the mean of a sample distribution of the sample means, the population standard deviation, sample size, and the sample mean. All right, so this is a lot of mean. Population mean mu, okay? The mean of the sampling distribution X bar, right? The mean of the sampling distribution of the sample mean is gonna eventually equal to the true population mean. Okay, that's what the central limit theorem guarantees us, which we know is equal to 606 minutes. All right, the population standard deviation is 62 minutes. The sample size, we know from the problem, we're gonna take a sample of 99 batteries. And the sample mean of that out of that 99 is gonna be the 619. So that's the number we need to convert into a z-score. All right, so the problem does say greater than. Greater than means I'm looking for at the area to the right. So for number 4, looking for the area to the right. So number 3, let's convert this into a z-score. So according to the formula, z equal to x bar minus the mu of the x bar divided by the standard deviation of x bar, which is equal to, I'm just copy that down, which is the simple mean minus the true mean divided by sigma over square root of n. So simple mean 619 minus 606 divided by 62 over square root of 99. So this is a little bit tricky to enter into the calculator because what you don't want to do is round, okay? Is do any rounding until the very end. So let me show you how to enter this. So basically I want the calculator to calculate the top first, then calculate the whole bottom next before they will divide. So in the calculator, I want to put the top in a parenthesis. So it will do that first, then divided by, then I'm gonna put the whole bottom operation in the parenthesis, 62 divided by. Now, when I do my square root, mine automatically come with the parenthesis with the square roots. So inside the parenthesis, I type in 99. So that my calculator is a little bit older version. I'm gonna close the parenthesis for the square root, and I'm gonna close another parenthesis for the denominator that I opened it. Run to 2 decimal place. So that's about 2.09. Right? So greater than, okay, it's wondering, what's the chance that, the true mean is 606 minutes. So if I take a simple 99 battery, what's the chance that the average battery life will be bigger than 619? So looking for the area to the right. So write out the computation using the graphing calculator. So that'll be normal CDF, looking for area to the right. So 2.09 must be my left bound, comma. The right bound must be to infinity, 1e99, comma 0, comma 1. All right, number 6, let's punch it in. 1e99, comma 0, comma 1. All right, so that's about 0.0 4 decimal place, 0.0183. So if you think about it, it's only about 1.83% chance that it's gonna be bigger than 619 minutes, okay? Because that's way above, right, the true population mean. All right, let's try another one, okay? The mean point obtained in an aptitude examination is 179 points with a variance of 225. What is the probability that the mean of the sample will be less than 175? If 77 exam are sampled, so we're gonna sample 77. What's a chance that the one I sampled it, the mean will be less than 175? All right, so this problem again, to satisfy the condition essential limit theorem, I think is again satisfied by the sample size at least 30. So I'm gonna copy this. If not, it's okay. No. All right. Sometimes they will say population is normally distributed too. All right, list the population mean, the mean of the sample, distribution of the sample mean, and the standard deviation, sample size, and the sample mean. So we know that because the central limit theorem is satisfied, we know the mean of my sampling distribution of the sample mean will eventually equal to the true population mean, which is equal to the true mean is 179 points. All right, so we got covered the first two. The population standard deviation doesn't give me that, it give me a variance. So variance is 225. So that means the standard deviation is square root of 225. Which in this case, I think is 15, right? You know what? Yeah, I believe so. Okay, but I'm gonna show you how to type. I'm gonna show you how to type this whole thing in there. All right, sample size is 77. And the sample mean I need to convert is the 175 points. So the formula earlier, right? I'm just gonna write the backside. Okay, I'm gonna write this backside version. So Z equals mean minus the true mean divided by sigma over square root of n. That will be 175. I need to convert minus 179 divided by sigma is square root of 225. I know it's 15. I'm gonna show you how to type this. 225 divided by square root of 77. All right, square root of 77 is gonna be something crazy. So we want to type all this together. Again, the top subtraction, put it in a parenthesis. Divided by the whole entire operation in the denominator, open a separate parenthesis. My square root of 225 is gonna give me an open parenthesis, 225. I'm gonna close the parenthesis for my square root, then divided by square root of 77. So my square root open the parenthesis for me. I'm gonna close the parenthesis for the square root of 77. Then I'm gonna close the parenthesis for the entire denominator. Okay, round to 2 decimal place. So negative 2.34. All right, so this one says less than. So that means I'm looking for the area to the left. All right, so left of this negative 2.34. So my left bound gotta be negative infinity, normal CDF. Negative 1E99, comma, upper bound is negative 2.34, comma, 0, comma, 1. All right, let me put in the calculator. Okay, about 0.0096 chance. That's not even 1%. That's not even, that's actually 0.96%. Okay, chance that happen is very unlikely. Alrighty. All right, this one is a little bit interesting problem. Okay, the mean life of a TV set is about 119 months with a standard deviation of a 13 month. Okay, if a sample of 67 TV is randomly selected, what is a probability that the sample mean would differ? The sample mean would differ from the true mean by less than 2 months. All right, so that part is a little bit weird, what that means. So again, number one, the size is 67. So again, I'm satisfied the central limit theorem by simple size at least 30. Okay, so the population mean, the mean of a sampling distribution. So we know the mean of the sampling distribution of the sample mean is going to eventually equal to the true mean based on the central limit theorem, which is equal to 119. We know the standard deviation is population standard deviation is 13, true population standard deviation. All right, we know sample size is 67. So what is the sample mean I need to convert? And that's what this differ from the true mean by less than 2 months. So what that mean is most of the people will say less than 2 months will be 117 months. That's true. That's only half of it. Okay, it's really trying to say it's differ by 2 months. So 2 month Lingways. Okay, so that's actually 2 months less, 2 months more. So the mean I'm actually trying to convert is actually 117 and 121 months. Differ by less than 2 months. So less than 2, that word less than, it does not mean that this word less than actually does not mean to the left. It actually means within 2 months. Okay. Because what's happening now is the true mean is at 119. So differ by less than 2 months. So that means within 2 months of that 119. So that's 117 and 121 are within 2 months. Okay. Of that 119. So I actually need to convert both of these z-scores. So this problem, I'm actually looking for the area in between. Okay. Differ from the true mean, differ from the true mean by 2 months. So the distance from 117 to 119, 121, 119 is both 2 months. Differ by 2 months. That means within the 2 month time. All right, so I'm just gonna write it out. So it's my z-score. All right, the simple mean 117 minus the true mean divided by standard deviation over square root of 67. And the other one is 121 minus 119 So the distance to the true mean is exactly the same, right? Whatever whatever one z-score is will be a negative, the other one will be positive. All right, I'm gonna put the top in the parenthesis, 117 minus 119. Divided by open parenthesis for the whole entire operation for the denominator, 13, divided by square root of 67. Close the parenthesis for the square root and close the parenthesis for the entire denominator. Negative 1.26. So the other one, if the 117 is negative 1.26, the 121 got to be positive 1.26. All right, same equal distance to the true mean. All right, so normal CDF, I'm looking for area in between with differ by 2 months, negative 1.26, 1.26, comma 0, comma 1. So the probability that the sample that I took, okay, the sample mean that will be different by the true mean by 2 months. Out of the 67 TV I randomly selected, okay, the sample mean will be different. The probability that sample mean will be different from the true mean 119 by 2 months will be about 0.7923. About 79% chance that it will be different within that 2 month period. All right, so just real quick, kind of introduce what is a central limit theorem and how we can use a central limit theorem to talk about this thing called the sampling distribution of your sample means. Okay, the whole idea is to take lots and lots and lots of sample. Okay, therefore we're going to have lots of different sample means. But the sample mean, these sample means will be very different since since we're taking so many of them. So it's because they're going to become very different, each sample mean is different, then they can become a random variable. So then we can use an idea of a central limit theorem to help us to say, okay, the mean, the population mean of the sample means that I took will eventually equal to the true population mean. That's the whole idea up here, is taking lots and lots of samples. So eventually we can actually approximate, okay, what the true mean is. All right, on the homework is pretty much what I just went over. Question number 1, enter the third characteristic of the central limit theorem from the lecture handout. So that will be up here. Okay, enter this one in the lecture handout, please. And I think the other homework question is basically the same. So yes, the quality control one. So for number 1 here, just to type satisfied by, the size, the sample size at least 30. Okay, if that's the case. Sometimes they will say it's normally distributed. This is a hospital question. Just 2 problems or just 3 questions here. Alrighty, thank you for watching.